Our research investigated an unknown dye using a spectrophotometer to measure absorbance and ultimately concentration of that dye. A spectrophotometer is used to measure the intensity of light or amount of photons absorbed after it passes through a solution. This can then be used to find the concentration of said solution. Our experimental design included shining a flashlight through a cuvette containing a substance. The light then transmitted through that material was interpreted via the spectrophotometer. The data collected through this process was then interpreted on Excel to find absorbance of the dye and to find the dye coefficient, and then the concentration of the dye using Beer's law. A cuvette containing fluorescent fluid was also investigated. Important concepts involved in this experiment show how photons move as a wave and as a particle. The photometer works by observing how the photons hit particles in a dye and starts vibration of the dye particles where there is a transfer of energy. Electrons then jump energy states and return to the ground states. Emittance is the energy released after the electrons in the dye particles drop back down to the ground states. Excitation photon has more energy than the emitted photon. In the experiment, water was used as the baseline for absorbance.
This graph shows the intensities as displayed by the photometer. Water, the baseline, should theoretically be greater in intensity than the rest of the materials at every spot. This is not the case, likely due to environmental light picked up by the photometer. The dye absorbance graph was created using the log of the intensity of water divided by intensity of the dye at each given wavelength, resulting in this yield. Comparing this absorbance to the known spectra, we determined that our dye must have been Swateli dye, as its peak is around 500 nanometers. This dye has an extinction coefficient of 27,000 1/molarity centimeters. Using the known peak absorbance of about 0.76, the extinction coefficient, and the width of the cuvette over the distance between light and the photometer, the concentration of the dye in the cuvette was determined in units of molarity. This makes sense because it would take very little dye to create a potent color effect. Here represents the intensities of fluorescein directly through the light, as well as when monitoring fluorescence by shining the light at a 90-degree angle to the photometer, so as not to capture any direct light. This graph shows a comparison of fluorescein absorbance and fluorescence, with the fluorescence graph downscaled by 100, so that it could fit on the same graph for comparison.
The graph on the previous slide shows the absorbance and fluorescence of the fluorescent dye. It can be seen that the wavelength emitted from fluorescent is longer than the wavelength going in. This is due to a loss of energy. The figure to the right shows this process on a molecular scale. A photon can cause a molecule to enter an excited state. Then when the molecule relaxes, some of the energy was used or transferred, such as vibrational energy. Then when the photon is emitted or fluoresces, the wavelength is longer because there's less energy. In order to get a reading on the fluorescent, a flashlight was placed at a 90-degree angle from the spectrophotometer in a darkened room. This was done so that the spectrophotometer only picked up the light emitted from the fluorescent and none from outside sources. If the flashlight had been head-on, the spectrophotometer would have been measuring the wavelength of both the emitting photons and the photons that were exciting the fluorescent. Since each substance has a unique spectra, spectroscopy can be used to identify different substances by looking at the patterns made by absorbance and intensities. When calculating the concentrations for our dye sample, we used the peak absorbance to identify the dye and then plugged it into the Beer's law equation. The absorption and fluorescence spectrums are different because absorption involves light being absorbed by an atom, whereas fluorescence is light being emitted. This process can be used in multiple different lab settings. For example, if you get something to fluoresce, you can use it for imaging because fluorescence makes things emit light so you can see them. This can't be done with absorbance, but you can use absorbance to identify certain compounds if it's a compound that doesn't fluoresce. Errors could have been made in the setup of the lab. For example, the intensity was measured multiple times in order to get more desirable data, and the positioning of the flashlight and cuvettes could have been altered in between runs. The light in the room varied during the experiment, so it could not be perfectly dark. This would cause other sources of light to interfere with the reading of the spectrophotometer, giving slightly altered intensities.